The next speaker is Alex Barnett, who's a research scientist group leader in CCM, and he's going to talk to us about FINFD non-uniform FFTs. Thank you very much.
Thank you, Jason. It's really fun to be back at what's now the 5th FWAM in the sequence. So, and I've really enjoyed the talks and so far, and what I'm going to say maybe will reiterate some of those things. I'm going to talk about my experiences from developing a small numerical library and what I learned, and I'd like to thank a lot of people who've contributed to this, including Melody and Andrea, who are both summer interns, and Joachim, who's now a consultant, who used to be here, Jeremy, Ludwig, Robert Blackwell, who's at SCC, and lots of other people. So, okay, so I'm going to define what there'll be a bit of math in the talk because we haven't had enough, I feel, so far. So, but it's one thing is you'll learn what this tool does. Maybe it's something you could use in your application. So, what is a one-dimensional type 1 transform? What does this do? In broad strokes, it takes this set of spikes. They're sort of sitting at arbitrary locations from -pi to pi, so like a periodic interval. And they have, those are the x's, and then they have certain strengths. They're like, you can think of them as little delta functions. Okay, and then here we have 6 little delta functions, and the transform's going to spit out 10 Fourier coefficients. It's literally the Fourier coefficients of that set of delta functions. So the Fourier coefficients are going to be called F. And so here's the formula, right? Given a set of M strengths, locations, and X, and a set of strengths C, then you're going to return capital N of these Fourier coefficients Fk that are just given by this exponential sum. And there's n outputs and there's m terms in each sum, so naively it should be m times n. It's got a quadratic cost, but and you'll notice if we happen to choose regularly spaced grids, a regularly spaced grid for those non-uniform points, you recover the old FFT definition. So this is a kind of off-grid version of the FFT called the non-uniform FFT. And it does this fast, meaning almost linear time, linear in the number of input points and the number of modes you want. So the other thing is you get the answer only to some user requested accuracy, like you might want only 3 digits or only 14 digits. So, and you pay a little extra cost when you do that. And then there's another type of transform, which is the type 2, which is its adjoint, but not the inverse in general. So, and so here you have the modes going in, Fk, and you have some other things sort of, which are like reading off a Fourier series at a bunch of arbitrary target points. And then the third type of transform that I won't say much about is a non-uniform to non-uniform version that you have arbitrary frequencies going in, and you have strengths. Sorry, you have points non-uniform going in, you have frequencies non-uniform coming out. Okay, so that was 1D. We also need 2 and 3 dimensions. So I've sketched what the 2D one looks like. So it sort of generalizes as you might expect. The non-uniform points sit in a box now, and there's still m of them, and then they're going to go and output a uniform grid of Fourier coefficients. So that's Fk, comma L. You can do it in 3D. You're already noticing, well, we've got 3 dimensions that we care about, most applications, 3 transform types. So that's 9 different transforms we have to think about. How are we going to avoid code repetition there? We also want to do it at 2 precisions generally. People in scientific codes like to either save RAM or maybe get a little extra speed sometimes with floating point with 32 instead of 64-bit floats. So how are we going to maintain 18 functions? Something to think about. Okay, So who uses these transforms? What are the applications? A main one is Fourier imaging reconstruction. So this is where those Fk, Ls are the unknown intensities of a grid of pixels. So, and the apparatus does some Fourier imaging, and it actually gets those Cj strengths that we talked about. So this happens in MRI. It happens in coherent diffraction X-ray imaging. It happens in astronomy, very long baseline interferometry, radio astronomy. It happens in cryo-electron microscopy. So there's an example of some of the non-uniform points in a 2D MRI application. Another application is forward solvers, simulation. So you can think of these non-uniform points as point of charges sitting in electrostatic in a box, and you want to do electrostatics. This is a little like what Vikram was talking about, figuring out the energy of a set of charges like this, or the forces on those charges. And things, PDEs become very simple over in Fourier space, so you want to be able to go back and forward to Fourier space. You can use these for numerical, for interpolation between overlapping grids, something David Stein has used this code for a bunch in CCB. You can evaluate Fourier transforms using quadrature approximations. And then I have an application that performs Fresnel diffraction, so optics application. Another category, sort of final category, is spatial temporal statistics. In 1D, you might be interested in getting the power spectrum of a time series or looking for periodic signals, periodograms in astronomy. You might be interested in the power spectrum of a clump of galaxies. And we have an application in Gaussian process regression, where the kernels can be applied in the Fourier domain fast. OK, I'll just show you one example. This is, on the left, probably the most famous astronomy image of 2019. And that is your unknown uniform image grid, Fk, L. Right? It has a resolution of, I don't know, 200 by 200. Oh, and by the way, the actual resolution is clearly not that good. However, it's kind of amazing in absolute terms because it's 10 to the minus 10 radians, because you're using telescopes that are scattered across the whole Earth and at wavelength of 1 millimeter. That's a big ratio. And here is the non-uniform points, and they are all of the pairwise in-plane distances, displacement vectors between all of those telescopes over time as the Earth rotates. So let's call those predicted signals GJ at each of these non-uniform points. And our library was a dependency and used to do the non-uniform part by the Smiley code in 2019 that was used to make this image. I didn't find this out until about a year or two later, and that was by randomly Googling one of the words in our code and noticing it was also in this repo. And then notice they didn't bother to tell you. That's the joy of successful open source software, I think. So, okay, so just briefly, what goes on here? You can write this image to signal map as a linear. It's a big matrix, right? It's a linear map. So G goes to F goes to G. Okay, and then what they do, and this is common to Fourier imaging applications, is you iteratively optimize some objective function that involves the predicted signal minus the detected signal, and then you do some regularization terms, and then every time you want to apply the matrix A or A transpose, you use the NUFD. Okay, so here's what happens, what the code actually does under the hood. So it's the most sort of common algorithm. And my boss is one of the people who sort of systematized this algorithm and expressed it. Let's just talk about 1D type 1 again. So what you do is you first set up a new grid in the spatial domain from, like, say, 0 to 2 pi or something. And that's actually going to have a little bit more points than you want to know the answer, than the number of modes you want. So let's say little n is 2 times the number of modes you want out. Okay, you then have to design a kernel function. That's this psi. And there's a beautiful math problem there that says can I make a psi that has a small width measured in these grid points, and yet its Fourier, the tails of its Fourier transform are epsilon small. Remember, epsilon is the tolerance you want the answer to. And if you keep those tails small, and I'm brushing under the rug a ton of analysis, then you can go and read the papers, including my paper sort of about this. You can do, there is optimal sort of design of a function, of a spreading function problem there. Once you have this good spreading function, what you do is you take these spikes, remember these are the input spikes, and you spread them onto the regular grid, which are these black dots, using these kernel functions. That takes a bunch of flops, especially in higher dimension. It's the width of the kernel to the d time for every point. So that's a lot, and it often dominates the cost. You've got to evaluate these kernels at arbitrary points as well. Okay, then the second step, you do a Fourier transform, a plain FFT of those black dots. And then you have a final step that kind of undoes or corrects for the fact that you spread out those spikes, and you divide by the Fourier transform of the spreading function. If you know your convolution theorem, that will make sense. And then you just keep the modes that you care about, and through clever design of the spreading function and the upsampling ratio, and you can make it have the accuracy epsilon that you want, and not waste any more time spreading to a larger number of points than you need to. Okay, type 2 is the reverse of this. Type 3 is type 2 wrapped inside a type 1. Okay, it's a nightmare, a bit more of a nightmare to explain type 3. I'm not going to go there. Okay, let's do some history. Like, how did I get into this? So prehistory, 2015, Leslie Greengard, Jeremy Magland, Marina Spivak, and myself were all recently arrived at SCIDA, Simon Center for Data Analysis, and I recently, because it had only just been founded, like less than 2 years before, by Leslie. So, and we were working on cryo-EM imaging, and we needed non-uniform FFTs, and we had this NYU code that Leslie had worked on like several years before that used a Gaussian kernel, which happens not to be optimal, but that was that, and it was single-threaded Fortran. And then there's a German code called NFFT3, which was multi-threaded but hard to use, and the user gets to choose the kernel, and why should they? So we wanted a multi-threaded code that we could use from many languages, and that's fast. Okay, so Jeremy started that project and wrote a spreader and a comparison of a couple of codes. 2016, Flatiron Institute founded. Just to like put this in perspective of kind of where we are. This is why this was early. Okay, 2017, I kind of got excited about this and wrote the first version of FineFD, building on Jeremy's idea and code, but I'm a C Fortran MATLAB programmer. So just keep that in mind, because it meant I wrote C++ like it's C plus pass by reference. And that was literally it. Like everything else I didn't really know about C++. I didn't know about vectors, classes, or namespacing, all of these things. So they kind of had to get them learned and professionalized. And that's a kind of probably something everyone will do when they try and make a library that other people are going to use. Okay, so I found this nice spreading kernel, and I thought it was faster than others to evaluate. It turned out to be wrong, but we don't know that yet. It's in 2017. Okay, so language wrappers and a GPU code get written over this period, and things get gradually professionalized as more and more people sort of come and get involved. Now we have like 200 GitHub stars and sort of dozens of known users. And I recently learned that someone has run the GPU code on 6,000 A100s. So that was kind of fun at once. Here's a lesson. Don't trust your gimmick, keep a change log. This is an old style documentation of like what changed, what you did. Don't trust Git commit messages. It's just not enough to go back and understand what happened. And I say small library here. The library is about 3,000 lines of C++. So it's that I still feel it's a small library. Let's dive into some stuff about it. Yes. They are using this for something called particle in Fourier methods for plasma kinetics. And it's like particle in cell, but they've realized Fourier representation is better, although still only second order, at best convergent, that kind of thing. So it's basically national kind of plasma style. It's a German group, but it's for simulating plasmas. Yeah, that's all I know. Okay, so let's get into performance aspects. So I was very happy that I'd made a kernel that required exp as the main operation. However, but that was not that fast. If you have GCC, you only get 40 million evaluations per second per core. So then it was suggested to me, actually by Vladimir Rocklin, that a piecewise polynomial approximation would be a much better way to evaluate this function. And then so I wrote C code, I wrote MATLAB code to generate C code that spits out the coefficients of such approximations. And then Ludwig of Klinteberg, you'll see his name here, showed how we could basically kind of transpose this and write it in a way that SIMD vectorized very well, so that we now sort of got more like 400, so basically 10 times the evaluations rate of this kernel. So notice there's no SIMD code here. So this is one sort of design idea. Think hard about SIMD, but don't actually use the intrinsics. Of course, you're sometimes just trying to guess what the compiler's doing. That's hard. Okay. Wendell Zhu and Robert Blackwell are exploring custom intrinsic code, which probably will be even faster, but it's harder to maintain. So that's a trade-off. Okay. So here's another performance thing. I learned this from Jeremy, that if you bin sort the non-uniform points, then you can get much better throughput. That's because RAM access to arbitrary locations in DRAM is bad, and you want to do them more sequentially because it comes into cache and then sits in the cache. Okay, so you process them in the bin ordering, and then we multi-threaded that. And just to give you an example, this random amazing software engineer in Germany just sped up my bin sort just because he was bored one weekend. That's the kind of stuff that happens, again, if you sort of have it facing to the world, and that's nice. Okay, there's the sort of load balancing and aspect. Interpolation, sort of the opposite of spreading, parallelizes well an OpenMP. Writing to an output grid doesn't parallelize well because the threads collide. So you actually have to write to a smaller box. Each thread writes to its own box, and then every now and then you copy 10,000 points over to the main grid. Okay. The interface is an interesting issue. I wanted it to be really simple and familiar to C and Fortran users, and to actually the interface kind of what do you call this template? I mean, function definition came basically to match this old NYU code. Signature, that's the word. So this is how you drive this from C++, but you'll notice it looks a little weird. We set up some vectors, but then we pass the pointers to the vectors in. That's because the thing is a C-compatible interface. And that's a really good thing. And we learned that from Brian's talk yesterday. Then that makes things easier down the line. This 1E9 is the tolerance that you wanted, right? The epsilon. So that's a pretty simple calling sequence. Oh, and there's this null thing. Why do we have the last argument null? That's because actually you could send in a pointer to an option struct that would then let you set debug options and various other like advanced user options. You have to have something like that, but you still want to always have an eye to simplicity for the new user. For someone who just, in half an hour they want to get something going. Okay, so then we realized that it's a big waste of time if the user wants to do the same transform with the same multiple data with the same set of non-uniform points. You should batch that up. So Melody, she and her internship started out by making these new interfaces. They're great. They run several times faster if you have multiple transforms for reasons that basically we are a driver to our main dependency, which is FFTW. Bless you. And that you only have to do the sorting once. So it seemed like a good idea. Okay, 2020, it's getting pretty painful. Remember, we had 18 functions. Now we've got the many versions of them. So that's like 36 functions. This is just too painful to maintain. So this led to the idea of a guru interface, which we did in 2020, built on Andrea Meleo's internship. Basically, and this is a common pattern, you create a plan, you set up the non-uniform points in this case, you execute one or more transforms, and then you destroy the plan. Ironically, this was exactly the kind of complexity I was trying to get away from with the German NFFT3 code. But it's better in the end. So you have this plan object, and as Brian described yesterday, so if you didn't see his talk, go and check it, because it's got sort of beautiful, simple illustration of this. You have a pointer to a struct, to a private C++ struct that the user doesn't really see. I'm not going to show the code for it, but you can call it an opaque pointer because the user doesn't get to examine the contents inside there. They just get to pass it around as an 8-byte pointer. So, okay, one lesson is learn about public versus private headers and namespacing. I had to learn all this. I didn't know any of this 3 years ago. Think about the interface and don't break it very often, very rarely. And this helps users, right? Oh, and by the way, so we wanted to keep this 36 interfaces, but what they do is they call the guru interface now. So we didn't lose them. We sort of changed what happens under the hood. And that's important to preserve your interface, but it actually got simpler under the hood. Okay, so other languages. There's so much I want to say that I'm not going to be able to, but this idea of a guru interface with 4 functions means you just wrap those 4 and pass around this pointer. And that made the language interface to multiple high-level languages easier. So, and actually then end up writing the simple and the batched interfaces in the high-level language, because it's just a few lines. So, and that's maintainable. So, for instance, in MATLAB, we have 9 little simple routines that just call the guru interface. So here's what the result, though, is. The user doesn't know that. They just do a beautifully simple call like this. They send in the data, they get the answer back. Okay. I still recommend, and people argue, but there's this thing called MRAP that David Bindell wrote, and actually some friends of ours maintain, including Libin Liu here, to auto-generate the MEX code horror that you need to interface to wrap those guru C functions. Okay, Python. Dan Foreman-Mackey here at CCA wrote PyBind 11 wrapper to FINUFTY, and this worked for a while, but it forced us to recompile the library, things like that we didn't want to do. So Joachim and then switched us to C types. This will echo what Brian talked about yesterday. It's only 1,000 lines, and that includes all of this crazy auto doc generation stuff that Joachim did, which I don't understand. And that's what also happens when multiple people work on a project. So, okay, I'll mention some other wrapping of FINUFTY to auto-diff frameworks that Steve was talking about yesterday, including a local one, PyTorch FINUFTY, that Michael Eichenberg has pioneered just recently. Okay, Julia sits in a separate repo. That's great. Separating concerns is good. The lesson, though, every language you try and support brings sort of installation troubles throughout time as languages change and versions change. And then there's 3 operating systems. If anyone's tried to work with MATLAB on a Mac, you'll know what I'm talking about. So I don't know how to solve that. And I hope that's one of, it'll get us to think about these things. In a sense, this question it's like Vikram's point. Can we build what I wished existed before I started, or that should exist, is like a template of like just some really simple array in, array out C++ scientific libraries, and then how to wrap them in all languages in a way that stays maintained, so we don't have to keep reinventing this wheel. And I don't know how to do that yet. Okay, testing. Obviously, you'll have tested every routine mathematically as you built the code. Otherwise, you wouldn't be a successful numerical code developer, but you then need things that test it to kind of test everything at once. And this includes a bunch of edge cases like sending in 0 points or requesting 0 modes and stuff like that. It's amazing the number of like things I found by writing a dumb inputs tester like this. But you have to do that. Okay. Another thing is sort of human readable output that shows timings and accuracies. And this is kind of what I use in a day-to-day when I'm trying to speed things up. And there's more output that you would maybe ask for, but and you can get if you go into debug mode, it'll spit out testings of the 3 steps, timing, that kind of stuff. Okay, but we want to make it pass-fail. So this is a story, right? I wrote these human readable tests. This was my tradition coming from scientific computing. Write this stuff and look at it with your eyeball, and that's sufficient. But then we kind of needed pass-fail tests. So I said, oh, I know the right thing to do. Pipe this text output to something called numdiff, which is a Linux tool that checks whether this number is small enough, let's say. Okay. 3 years later, Mac and Windows users cannot find numdiff. Upshot is we have to rewrite the tests so that they just spit out 0 for success or 1 for fail. And that is the way I recommend you do it from now on. Don't have any non-essential dependency like this. Even just one innocent little Linux script kind of style tool ruins everything for like trying to get this to be accessible to different users. Okay, make the tests for each language, use continuous integration. And we're trying to, we sort of transition to CMake, but I don't want to give up the alt make file because people use the alt make file. Okay, documentation. Here's the web page. It's essential to have it sort of web facing for professionalism. There's a lot of categories. I wrote a lot of this myself. Math definitions, installation instructions, examples, tutorials, so forth. They're all kind of essential if people are going to use your code. I mean, you can do it in a readme.md too, but this is probably better. Okay, a decent solution I recommend is this Sphinx and then hosted at Read the Docs. This use restructured text, and then you get pretty good LaTeX rendering with formulae, which we all need. Okay, single source of truth. Don't repeat. Try notice when you're repeating documentation. In fact, I moved all the documentation out of the source code. The source code says, see the website for documentation of this function. Don't get carried away with trying to automate everything, though. It's a trade-off. I cannot now understand the bash script that auto-generates some of these docs because I wanted to save writing like a description of the tolerance parameter 36 times. But now I don't understand how that code works if I want to change it. So, okay. Describe what your tool does in plain mathematical language. This is a big one because there's a ton of language code that says, the k-space points or the wave function, this, that, and no math definitions. You have no idea what it does, and you can't use it in another application. And always update the docs at the time you change the source. And this is hard to do in a team. And GitHub issues, well, we need to find a way to make that happen, but it usually happens. Okay, I'll mention the GPU version, and you'll actually see a little performance plot of like 90 seconds. So Melody Shi wrote this. She was an intern here for 2 summers, and then I think partly based on this, got a job at NVIDIA in the QFFT team. And so these are the GPU codes. We're showing nanoseconds per non-uniform point. So this is, 3 nanoseconds means you're getting, 300 million points per second. This is the CPU code. It's like sort of 10 times slower. These are some other GPU codes. They're slower than the CPU code. But things are, catching up. This is always sort of evolving. This is from the paper a couple of years ago. Robert Blackwell has recently done an amazing job of cleaning up Melody's sort of research code into the main repo, and we don't, we're sort of just trying to decide how can you bring those 2 codes. You can imagine this is like the evolution tree. Things split. Can you merge them back together? Can we auto-detect GPU arrays in a more elegant interface that's switchable? And here's the conclusions. So developing a small-ish library. I would say the library is small. the machinery around it to make it easy to use isn't that small. But first identified a need, and that means you have to benchmark existing codes. And that means you have to wrap existing codes. And even that is painful, but you have to do it. Can you perform it this task more accurately? If not, well, don't write a code. Okay, start small using what you know, right? But then you're going to end up, to professionalize it, you're going to end up learning a bunch of stuff you didn't think you wanted to have to learn. Users will find bugs that you'd never thought of, and Libin Liu in CCM has been amazing at being the sort of first responder for bugs. They'll improve your code too, which is really nice. But for your own sanity, don't try and change too many things at once. Just don't let feature creep happen. Just, stick to one feature at a time. Try to be somewhat idiomatic. I was an idiot, and I wrote, macros. The whole code still in C++ has a C-style macro definition that switches the two precisions from float to double. Okay, go figure. But it works. I can understand it. C++ developers hate it. But if I would next time around, would template it. But I didn't know templating. Okay, collect a great team, software engineers, interns, motivated users, have meetings, prioritize features. Then installation, dependencies, and language wrappers takes much of our effort. But it helps engage the base. Oh, and by the way, in all of these wrappers, can you guess which language wrapper the black hole astrocode that was used for that black hole image uses? Any guesses? Yes, it's Fortran. So much for AstroPy. Anyway, that's what they used. So, and they use the makefile in Fortran. So I can't really remove the makefile. Anyway, there's still plenty of fun sort of with the math. I mean, all of this is sort of on the side of the math algorithm research and floating point speed hacking. So thanks a lot.
Really get your point for out of code documentation, because to me the point of inside code is you modify the documentation at the same time as a function, which is one issue you mentioned.
Yeah. Well, you just have to remember to do it. It's just in a different place. That's all. I don't find that too much of a problem. Maybe it's that the C++ interfaces haven't changed in a long time. But right, what we have is a developer notes section that kind of tells you where to look, what to do a little bit, and that helps.
But maybe it's me who missed it, but what was your argument for not using just a documentation inside the code, like each function comes with its own documentation?
Because I don't want to have to auto-extract them and pipe them to the website in a complicated bash script type of thing. And I don't want to have to learn Doxygen and, right? There's just, you have to limit the number of tools. There's a lot of tools out there and you can't learn them all at once. You spend your whole life learning them. So I just made a decision on that. And that's where they sit. And it says, see here for the docs. So I think they sit in text files in the end. The problem is there's user-facing documentation, and there's developer documentation. You can obviously put some of that in your source code. But the user-facing stuff sits somewhere else. It's a choice, but yeah. Vikram, looks like.
This is really cool. Obviously, one of the big selling points of your software is the performance scaling. Do you have a performance test that tests the scaling? Because you could conceive of a situation where some developer makes a change to the software that improves absolute performance in a particular case by, say, a factor of 2 or something like that, but ruins the scaling. Now it's quadratic instead of linear.
Yeah, or the scaling with cores is one of the main ones. I didn't show a plot of that, but yeah. I don't have automated testing. I mean, this is something I asked yesterday. Automated performance testing. I mean, what I do is every few months, I literally run those executables and paste the output into a file, which I sort of put in the repo as like the current performance on Alex's laptop. I mean, that's the level we're at. right? So it's not, I don't know how to automate that, but that helps you make a decision about whether to bring in a pull request or not.
Related to that, on the earlier point of having a library of Flatiron resources,
Yes,
just having a standard Flatiron way of testing software like this might be.
that would be great. Yeah, I mean, I don't know how to do performance testing in CI, but you can't run it every commit, every push to master. You can't rerun performance tests. So yeah, it looks like this.
So I've recently looked at this source code for reasons for trying to do something with it. But so my question is, are there any plans for the near future to kind of replumb these macros into templates or something?
Yeah,
more
yes,
maintainable by a wider array of people.
it's not urgent, but because Robert Blackwell can understand the templates, the macros right now, and he's sort of got doing some of that, is helping out with that work, and that's great. I don't know. It's not really needed. It's kind of like a lesson for next time. I don't think it's breaking anything. It's just not idiomatic C++. It was annoying. I mean, macros are horrible. You can get in some logical twists and stuff. So
okay, maybe in the interest of staying on time, we'll leave it at that. Thanks again to Alex.
thank you.